Now we look at the second part of the fundamental theorem of calculus, which says the area under a curve, namely this integral here, equals an expression using the antiderivative of the original function. If you recall, this area under a curve is a rather complicated limit of a sum of areas of rectangles, which can be very cumbersome to evaluate. However, now we can relate this area, this integral, this definite integral, to the antiderivative, which is a much easier calculation as long as we understand the derivative relationship for the given function. So this is rather profound that we can now simplify this area calculation down to just an antiderivative, and that's fantastic. So f is any antiderivative of the original function little f, and the original function little f is continuous. So the first thing we're going to do is we're going to, of course, use part 1 of the fundamental theorem of calculus. So note that if we define g of x to be the integral from a to x of f of t dt, by the way, the variable you use here is irrelevant. F of x dx and f of t dt are equivalent. I have to use f of t dt or something besides x here now because my function is of x and I need my variable now to be the upper limit of this integral for what I'm going to do. This function, g of x equals this integral, this area, is an antiderivative of the function f, because the derivative of g with respect to x is f of x by the fundamental theorem of calculus part 1. Okay? Now, f could be any, big F could be any antiderivative. Well, it simply must be g of x, right? G of x is an antiderivative, and both of them have the derivative little f, so f of x must be g of x plus some constant. They must differ by only a constant, okay? Now the constants, we're going to see that it's irrelevant. F of x is just this antiderivative in addition to some irrelevant constant. Now what we do is we prove this statement's true. So I'm going to start by looking at the right-hand side. F of b minus f of a equals, well, I'm going to use this definition for big F. F of b would be g of b plus c minus f of a would be g of a plus c. And when I simplify that, I get g of b minus g of a. Rather simple. Now I'm going to use the definition of g, which is here. G of b would be the integral from a to b, right? Replacing x with b, of f of t dt, minus the integral, g of a would be from a to a, of f of t dt. And of course, the area under a curve, when the point here, the x value doesn't change, the area under that curve would be zeroed. And so what we get is just this thing. And as I mentioned before, the variable with which we integrate, with respect to which we integrate, is irrelevant. So let's just make it look exactly like this now, which I can do because I don't have a t or an x on the upper or lower limits of integration. So from a to b of f of x dx. And that's exactly what we wanted to prove here. So to calculate an integral, to calculate the area under a curve now, we simply need to know the antiderivative and the limits, the starting and ending points of that integration. Okay, and then we'll plug them in to the antiderivative.